All right, guys, here's a review for our second assessment. It's a periodic table and periodic trends. First, we have a discussion about the different scientists who discovered different parts of the atom and formulated our current theory of what the atom is and how it's put together. Our first one is Mr. John Dalton. He had the four postulates, as you can see right here. All matter is composed of small invisible particles called atoms, and he believed that they put together in even ratios and definite ratios. And again, we cannot create or destroy or convert kinds of atoms during different reactions. They're simply just rearranged. And so here's kind of an example of what his atom might look like. I have a carbon and oxygen if I put them together in different whole number ratios. Again, that is Mr. John Dalton. Next up, we have Mr. J.J. Thomson. He came up with the plum pudding model. He discovered the electron using cathode ray tube experiments, and he theorized that the atom is kind of like a bowl of plum pudding, or I call it like fruit salad, something like that, or jello pudding. So you have your atom is just one big giant circle, and your electrons are just randomly placed throughout inside of it. Next up, we have Mr. Ernest Rutherford. He developed the concept of kind of an empty space model using his gold foil experiment. And basically what he did is he fired alpha particles at a sheet of gold foil, and most of the alpha particles went straight through. Only a few of them actually hit a positive object in the middle of the nucleus, which he later determined that was called the proton. But again, he decided that most of the atom was empty space. And so the atom is a very large substance with a very, very small positive nucleus in the middle, which he called the protons. Next, we have Mr. James Chadwick. He came up with the idea of the neutron. He decided that there was something else inside of the nucleus that had mass, but also had no charge. And so he decided that the nucleus not only contained a positive proton, but again a neutral substance called the neutron. Next two gentlemen I don't have pictures for, but Mr. Schrodinger, he came up with we call the wave equation or the Schrodinger equation. He came up with this idea that the electron traveled as a wave throughout the atom instead of just a particle. And our last one here, Mr. Heisenberg came up with the idea called the uncertainty principle. Basically what he said is you cannot know where an electron is or how fast it's going. You can know one or the other, but not both. Oh, excuse me, I think I skipped one. Mr. Niels Bohr. Again, sorry, here's Mr. Niels Bohr. He developed the idea of the planetary model, that electrons are in fixed orbits around the nucleus, similar to where the planets go around the sun. So you have electrons that are closer to the nucleus, like Mercury is closer to the sun, and then electrons that, again, are in levels in different levels further away from the nucleus. So again, it would look like this. So I have electrons that are traveling around a first level, second level, third level, so on and so forth. You might have seen this representation if you've ever seen shows like The Big Bang Theory or Jimmy Neutron. Again, it's a rather simple way to understand the atom, but again, it is incorrect. And those are our atomic theories developed by the scientists over time. Next portion of the review deals with the relationships between energy and frequency, talking about the electromagnetic spectrum. The first one is what is the relationship between energy and frequency. We call that a direct relationship, meaning that as energy increases, so too does the frequency. The second question between frequency and the wavelength. This is an indirect or an inverse relationship. As the frequency is going to increase, your wavelength is going to decrease. So again, it says the frequency is going higher, the wavelength is actually going to get shorter. And here we have a question about the electromagnetic spectrum. We're going to list the following types of radiation in order of increasing energy. So we're going to start with the one with the lowest amount of energy. That would be a radio wave. So because it has the lowest energy, this one will also have the longest wavelength. So after radio is going to be our infrared, followed by our visible light, followed by X-rays, and lastly would be gamma rays. So if we think of it this way, if radio has the longest wavelength, gamma ray would have the shortest wavelength. Since gamma rays have the highest amount of energy in the spectrum, radio would have the lowest amount of energy in the spectrum. So here we put it in an actual diagram. Amplitude is how tall the crest or the troughs are. So this would be the amplitude here. And the actual length from one crest to another, or again, one point on a wave to a similar point, would be known as the wavelength. Skipping down here, we're talking about the periodic table and how it was arranged. Mendeleev, he did it by atomic mass. And he left spaces in the periodic table because he kind of arranged it by atomic mass and also in vertical columns according to their chemical properties. And the reason he left spaces is because elements that had not been discovered yet should have belonged in those spaces. They just hadn't been found yet. So then Moseley came along and he arranged it by atomic number, or we also know as the number of protons, and that's the way that we have the periodic table today. All right, guys, now we're going to talk about the different parts of the periodic table, what is included in them, and their properties. Our first is metals, and we're going to say they are left of the zigzag, and they are shiny. They are great conductors of electricity, and they are also malleable, which means they can be shaped and formed to form different objects. Nonmetals, they are right of the zigzag. They are dull, poor conductors of electricity, and they are considered to be brittle, which means they're easily broken into small pieces. And our metalloids, they are along or on the zigzag line, which I'll show you here in just a second. They are shiny. We call these semiconductors, and they are also very brittle. Now, a good way to remember, if it's a metal, we call it shiny. And so here is our zigzag line on the periodic table. You guys did this in your periodic table activity the other day. So again, if I am an element that is left of the zigzag and considered a metal, and if I am right of the zigzag in this upper right-hand corner, I'm a non-metal, and the elements right here along this zigzag line are considered our metalloids. Moving on to the next section, we're going to classify each of these following as metals, nonmetals, or metalloids. So bromine is to the right of the zigzag line, so that's going to be a nonmetal. Gold is over here, element A79, AU. It is to the left of the zigzag line, that's going to be a metal. Now boron, he is on the zigzag line, boron the moron, so we're going to call him a metalloid. Helium, upper right-hand corner, he is to the right of the zigzag line, that's going to be a nonmetal. Rubidium is way over here on the left-hand side. Right here, element number 37 is in column 1. That is a metal. And then plutonium is also going to be considered a metal. Last section here on page 1 talks about the periodic trends, atomic radius, ionization energy, and electronegativity. Now, as you guys remember from your notes, what we have to remember is the pattern for atomic radius, and just know that ionization energy and electronegativity are opposite. So our first one here, increasing atomic radius. Our biggest elements on the periodic table are in the lower left-hand corner. So francium is a friend to you and a friend to me, and he's really big, you see. That's how I always remember it. So the closer I get to francium, the bigger my element is. So if I'm going up a period or up a family or across the period towards helium, my element is getting smaller. So here lithium is the furthest away from francium, so we're going to start off with the smallest one being lithium, followed by sodium, followed by potassium, and again last would be rubidium. So same thing here, sodium, if I'm looking at my periodic table, so I have sodium, magnesium, aluminum, and chlorine. So we're working across a period starting sodium, magnesium, aluminum, and lastly chlorine. So chlorine is the furthest one away from francium. That means chlorine is going to be the smallest one. So we're going to start off with chlorine, then aluminum, magnesium, and sodium. So looking here at question number 9, if I know that the atomic radius gets bigger towards francium, ionization energy and electronegativity would then just be the opposite. So order of increasing atomic energy, the closer I get to francium, the smaller it's going to be. So this one is going to be actually backwards. The further away I get from francium, the higher the ionization energy becomes. So then it would be the opposite. Rubidium would be the smallest, followed by potassium, followed by sodium, followed by lithium. And same thing here. The closer I get to rubidium, which would be sodium, followed by magnesium, followed by aluminum, followed by chlorine. So last question here, question 10, increasing electronegativity. This is going to be the same exact trend as our ionization energy. The further I get away from francium, so if I'm going this way on the periodic table, I'm going to increase in electronegativity. So I start off with rubidium would have the least amount of electronegativity, followed by potassium, followed by sodium, followed by lithium. And it's going to be the same trend here. The further away I get from francium, the higher my electronegativity was going to increase. So again, sodium will be the first, followed by magnesium, followed by aluminum, followed by chlorine. Now another way to think about electronegativity is fluorine, right here, she is the most electronegative element on the periodic table. So if I'm getting closer to fluorine, I am increasing in electronegativity. And the other trend, again, if francium is a friend to you and is a friend to me and is really big, you see, the closer I get to francium, the larger my element is going to become.